This is the second video on section 6.6, Lagrange multipliers. And in this video we're going to use Lagrange multipliers to find the max and min value of a function on, subject to a constraint. So in the notes it says maximize, but I wrote optimize here. So instead of finding the maximum value, we're going to find the maximum and the minimum. So we're going to optimize this expression subject to this constraint. Notice this is the unit sphere, right? X squared plus y squared plus z squared is equal to 1. And so we'll set f of x equal to x squared plus 4y plus z. Now remember, a continuous function on a closed bounded region has a max and it has a min. What we're going to do here is we're going to do something differently than we did previously. Previously, we would find the critical points, test the critical points, and test the boundary. Here we're going to use Lagrange multipliers, and in many cases it is simpler and faster. And so we have our function, and so remember from Lagrange's theorem, we want to maximize and minimize this subject to the constraint g of x, y, z equal to 0. So we set g of x, y, z equal to x squared plus y squared plus z squared minus 1. So if this is true, then x squared plus y squared plus z squared minus 1 is equal to 0, and that's the constraint we're working with. So we're going to let g of x, y, z be this sum minus 1. So now we're going to look for the Lagrange multipliers. So we're going to solve this equation. Gradient of f is equal to lambda times gradient of g. Calculate the gradients, so we just take the partial derivatives. And we're going to factor out a 2 just to make our coefficients smaller. So in the end we have the vector x2, 3 is equal to lambda times the vector x, y, z. Now, from the first components, we see the first component of the vector on the left is x. The first component of the vector on the right is lambda x. So we have the equation. Lambda x is equal to x. That tells us that two things are possible. One is that x is 0. The other is that lambda is 1. So let's investigate. If lambda is 1, then what happens? Well, if lambda is 1, let's come back over here. If lambda is equal to 1, then that means y is equal to 2 and z is equal to 3. That's from the second components of these vectors. That's what happens if lambda is 1. Well, then y is 2 and z is 3, but this isn't possible, or it's a contradiction, because x squared plus y squared plus z squared is equal to 1. It doesn't matter what x is. If y is 2 and z is 3, then we have 4 plus 9 here, and plus some non-negative number equal to 1. So that can't happen. So it is not the case that lambda is equal to 1, so lambda is not equal to 1. So now we know that x is equal to 0. Whatever point we're looking for, we know that x is equal to 0. We have to find the other two coordinates. So we go back to this equation. What do we know? Okay, we know that lambda y is equal to 2, lambda z is equal to 3, and remember our constraint. X squared plus y squared plus z squared is equal to 1. So we substitute. Remember, we've decided now that x is 0, so we have 0 squared. This is y squared plus z squared is equal to 1. This is just an equation with a lambda in it. Multiply through by lambda squared, we have a quadratic. Lambda is either the square root of 13 or the negative 1 times the square root of 13. So our quadratic equation had two solutions. So we look at the points. Remember, lambda y is 2, lambda z is 3, and now if lambda is negative square root of 13, here's our y, here's our z, and we calculate the function value at that point. We have negative 2 times square root of 13. The other possibility is lambda is positive square root of 13. So we substitute up here. So we have f of 0, 2 divided by square root of 13, 3 divided by square root of 13. We calculate that, and it is 2 times square root of 13. This is the maximum value of f on the unit sphere. This is the minimum value.